And yeah, so I work at Google DeepMind. So folks might know that Google DeepMind is the AI research lab within Google. Most of our people focus on advancing the kind of state of the art of AI research, but we have a dedicated science team as well that works on applying AI to scientific problems. So across biology, energy, weather forecasting, quantum chemistry, and also applying it to maths and computer science problems as well. And so what I'm sharing today is kind of an essay that we wrote about the AI for science opportunity. So first of all, kind of full disclosure, full caveat, I myself am not a scientist. I could possibly call myself like a lapsed economist at a stretch, but my working job is actually doing research to help two teams at Google DeepMind. So one is our public policy team, a team that engages with policymakers and governments about what they should do on AI public policy, so looking out the way. The other team I work with is our responsibility team. That's a team that looks at our models that are coming down the pipeline and tries to assess what are the benefits and risks to society from these models. And so what should we, Google DeepMind, do in response? So looking more internally. And yeah, thank you, Sophia, for the quick plug. We have this AI Policy Perspectives newsletter where we put out various kind of opinion pieces on AI policy. But really for us, it's a way to learn in public. So we get great feedback from people and great critiques from people, especially on those pieces. And we find that very valuable to us. So yeah, please do not just kind of read, but give us your take today and also after the session as well. Moving onwards, yeah, so the AI for Science essay that we put out, it was back in November. It's on our Substack. It was called A New Golden Age, Seizing the AI for Science Opportunity. And really what we wanted to do was tell a story primarily to policymakers, but to really anybody interested in AI for science about what is happening with the application of AI in science. Why should they care about it? And what should they also do about it, right? So our essay and kind of this talk follows maybe a 5-part structure. So first of all, we try to explain why we think there's an imperative to use AI in science, which is a strong statement. So we'll try to back that up in a second. Then we talk about the concrete opportunities to use AI in science and where we see the biggest opportunities. We then talk about some of the ingredients to do it well, both within individual research efforts, but also the ingredients you have to have in the broader science ecosystem for the application of AI to science to work well. We then talk about the risks as well. People have very clear risks, including scientists, that they worry about from using AI in science. We wanted to address those kind of head on. Then we end with basically policy ideas. If you're a policymaker who thinks AI for science is important, what concretely could you do about it? So I'll try to cover all this within 25 minutes so that people have a chance then to share your own takes. I'd be very curious to hear your opinions and of course, any questions. One note to say, when I say AI in this talk and in our essay, we're referring to modern deep learning models. Of course, AI more broadly, earlier versions of AI and alternative versions have been used in science for a long time. So we're focusing more on modern day. So yeah, first of all, why might there be an imperative to use AI in science? So we all know it's possible to use AI in science in your research. There's also other methods you could use, some of them cheaper, maybe more easy to use. So why is it actually necessary to use AI in science? There is a reason, and it's traced back to basically, in science policy discussions, there's a big debate still going on, about is the overall rate of scientific progress slowing down or even stagnating. It can kind of sound a bit strange to make that case at a time when we have new mRNA vaccines just a couple of years ago for COVID, when we have GLP-1 drugs, when we have AI progress itself, right? But actually, if you stand back a little bit and look at somewhere like the US, which has maybe the biggest, richest science ecosystem, over the past half century, the size of the scientific enterprise has grown quite significantly, right? So there's probably about 7 times more scientists working today than there was 50 years ago in the US. At the same time, some of the kind of impacts that you'd expect to see from that expansion in science don't necessarily appear to have materialized, right? So if you look at economics, for example, and productivity growth, which is the main ingredient for long-term economic growth, productivity growth in the US and other high-income countries around the world, and even lower-income countries, has stagnated badly over the past 20 years. Similarly, if you look at things like Sustainable Development Goals, the UN SDGs, these capture goals in things like fresh water supply, climate change, education. And There's been progress in some areas, but again, last 5 or so years, some worrying stagnation in some of these domains. And then also in some of the areas that are mentioned, maybe by Mukti as well, like drug discovery rates, crop yields perhaps, how many transistors can we put on a semiconductor chip? There are many applications of science where people are worried about slowing down of progress. Now, I think there's nuance to all those things. There's many reasons for those trends that go way beyond just scientific progress. I think the one thing we can say with some confidence is that to make a scientific breakthrough today, and certainly to deploy that breakthrough usefully at scale in society, you often need many more people than you did before. And we think the main reason for that is these two things on this slide, scale and complexity. So we think that many scientists working today face problems of scale and complexity all the time, right? Whether it's the size of the literature base they have to master, which not only gets bigger and bigger and bigger, but gets more and more specialized in each subdomain in terms of its language and so on. It's also in terms of the experiments you might want to run. Indeed, many experiments people want to run today, they can't run because it's just not possible for them to do it. And also in terms of what people study. So again, we have biologists on the call, so hopefully they can clarify this more. But like biology, at least to me as a non-specialist, it seems like the more we learn about it, the less we know about it in some ways. Like we realize just how complex it is, right? Like, so we keep peeling back layers of complexity. And I think this brings it back to why we think AI is important. We think modern deep learning models are particularly well suited to problems of scale and complexity. That's a little bit abstract. So like concretely, we wanted to map out what opportunities are we most excited about to use AI in science research. Now, our challenge here, of course, is that there are many scientific disciplines, many subdisciplines, running to the hundreds, the 200s. We wanted to provide a small number of opportunities that we think are genuinely, AI is genuinely additive to other approaches, and they apply across disciplines. So these were the 5 that we landed on, and I'll try and briefly explain them. So the first is around knowledge, so changing and transforming how scientists digest knowledge, but also how they communicate their own research to the wider world. So already from my side, I use Gemini in our case to summarize papers for me and to critique papers. Not perfect, but getting better quite quickly. And I think we're getting to a point quite soon where you could upload, let's say, 100 papers in a certain domain and not just get a summary, but get a sort of a critique of how the papers relate to each other, sort of an evidence synthesis. We're getting quite close, I think, to AI being useful to those use cases. And there's much more, of course, then to come. I think we've seen less progress so far on people using AI to communicate their research. You know, a few little examples, like we have our Notebook LM app at Google, people like the audio podcast overview. But I think, you know, my ambitions here will be much greater, right? I mean, the journal paper, the academic kind of style journal paper, I think has many, many advantages to it. That's why it's lasted so long. You know, it makes science indexable for one thing. But I think for many people who aren't themselves deep experts in the area the paper is talking about, the format of an academic paper is more of a barrier to enable it to engagement with research than it is a kind of enabler of that. So I do think we'll start to see scientists experiment with AI to share their research in more kind of creative ways. A second opportunity I'm very excited about is data. So we'll talk about, of course, the data you have to train AI to be useful in science, which is kind of maybe the biggest topic in this space. But there's also a neglected opportunity to use AI to create or perhaps to better curate scientific data. So despite having a bit of a deluge of data in some scientific fields, like in the life sciences, I think no scientist would say they have the data they want to have, right? And actually we have a real paucity of high quality data still across most disciplines, and especially for areas like the oceans or the atmosphere, or in social sciences like the informal economy. You know, we really have very little data. Now, AI won't be a substitute for investing in lots of different data generation technologies, and actually it's more of an argument to invest more in those other areas. But there are some things that AI can do that I think will be helpful. So one where we already see progress is you know, some small niche use cases around using AI to improve existing data generation approaches. So people have used AI to help reduce some errors or noise in how we sequence DNA. They're using it to help better detect cell types in a sample Again, none of these use cases are perhaps perfect yet, but it's all about reducing noise, error, etc. Another example that we're excited about, but is also quite difficult, is using AI to better annotate data. So again, in biology, for example, we work a lot in proteins. We have very kind of poor annotations for many proteins, including for the functions that we think they're thought to provide. Where we do have annotations, they're often either unreliable or have errors in them. And there's many reasons for that, right? It's not really incentivized work in many cases. But we've seen some examples for how AI can also predict annotations usefully for some of these data sets. But of course, the one we're most excited about, but is hardest, is using AI to generate like synthetic scientific data that is useful. Now, again, there's many challenges to doing this. You have to do it very carefully, but we're seeing like concrete examples now. So one of the areas I'm most excited about is protein design. So using AI to design de novo proteins. Our team recently put out a paper in this space a couple of months ago, and they trained that model using synthetic protein structures from AlphaFold, our earlier kind of tool to predict protein structures. So you're starting to see now a bit of a data flywheel kicking in, again, with caveats and challenges along the way. Third area is experiments. So as mentioned, lots of scientists today can't run the experiment they want to because it's too big, too complicated. They can't access the equipment or facilities, or they can't access the people they need to do it, right? So I think we're seeing some interesting examples of how you can use AI to simulate experiments. Now, generally, the goal here isn't to replace the experiment in the real world. It's not to do the experiment even in the same way as you would do it in the real world. It's more to inform those real world experiments so you get more impact and return on investment out of them. So one example here that we've worked on is fusion energy. So, fusion energy, the goal of generating fusion energy, super hard goal, might never happen, who knows? But at the crux of it is this need to control plasma. Plasma is this fourth fundamental state of matter. When you start reading about it, it's kind of mind-boggling as a non-scientist to understand it. But one of the challenges to working on it is it's very hard to get access to reactors to run experiments. There's lots of different reactors, but one example is the ITER, ITER. This is a nice example because it's an international collaboration, different countries coming together, investing in international scientific collaboration. But they're building a prototype tokamak fusion reactor. And they started building it in the early 2010s. And I think it's due to do the first large-scale plasma experiments in the mid or late 2030s, right? So you see the obvious sort of problem there, right? So our team did some research a while ago with some collaborators externally to use AI to control plasma in a simulated reactor. And there's a very interesting question right now around what other scientific facilities could you simulate really usefully for experiments, like telescope arrays, gravitational wave detectors, and so on. So I'm kind of very keen to see what happens in the next couple of years in that space. Moving briefly, I'll try to these last two opportunities a bit more briefly so we have time for the rest of the session. But the last two are basically around modeling complex systems. So obviously much of science, as I mentioned in the previous slide, ultimately comes down to modeling systems, whether in biology, in the economy, the weather, that are complex systems. That is, they have many, many interacting parts. Their behavior is dynamic. It's often random or somewhat chaotic. And if you intervene on it by putting in a new drug or by putting in place a new tax on the economy, it'll often respond in ways that are very hard to predict, right? And so we have all these traditional approaches to modeling these complex systems. They've been very, very useful, and they've led to great breakthroughs. But many of them rely on sets of maths equations or sets of physics equations. What you often see at some point is them breaking or not being sufficiently accurate. And so we're starting to see now examples of deep learning being useful for modeling these complex systems. So one of my favorite examples here is weather forecasting, which of course is, unlike other areas of science, is like useful to everyone. Everyone gets it, right? And we've seen last year or so deep learning methods outperforming, in some cases, traditional methods of weather forecasting that are based on sets of physics equations. So I think that's quite exciting. And the final opportunity then is around a similar kind of problem, which is basically around how do you find the best solution for a scientific problem that has many, many potential solutions. This is a common problem facing many scientists, right? So if you're designing a new protein, you got to choose your set of amino acid sequences. If you're designing a new computer chip, the combinatorial option space is like off the charts. If you're proving a maths theorem, there's actually many, many options, right, for the proof, right? So how do you pick the best solution? And so scientists historically often use intuition, very powerful thing in science, iteration, trial and error. But one of the challenges, of course, is that at some point, you can't really cover the full option space that you want to explore. And so we're starting to see how AI can cover more of the option space, but then critically can also kind of hone in on solutions that are both viable and useful. So for example, in mathematics, because often novelty by itself isn't what's important. It has to also be useful and viable. So in mathematics, we see people using language models to fine-tune language models to generate possible kind of constructions for a mathematical problem, and then using other AI models that are kind of grounded in mathematical logic to find the best solution from those kind of suggestions. So kind of combining different kind of powers AI can bring. So there are kind of 5 opportunities that we're excited about. We think apply across disciplines. The second thing that we talked about was then what are the ingredients that you actually have to have? What are the ingredients you need to have to do AI for science well, both in an individual research project, but then at the ecosystem level where policymakers can support certain things. So to do this essay, we interviewed about 30 odd people at Google DeepMind. We also interviewed a bunch of people externally, and we really pushed them to tell us the ingredients for success. And they gave us these kind of 9 ingredients, which we organized into a simple toy model that we call the AI for Science production function. So in the economy, the production function describes the inputs that lead to the outputs. And so here we want to do the same thing, but for the application of AI for science. It's obviously a very simplified model. Every effort looks different, of course, et cetera, et cetera. But if we start from the left-hand side, so the starting point is often having a very good problem and specifying your problem in a way that's very kind of practical and useful for AI. So here we often look for problems that, for example, have large combinatorial search spaces or large data sets and have very strong evaluation methods, which is the second ingredient. This is not true of all scientific problems, right? Then it gets to the question about the infrastructure that you have to do this work. And here, I think the key infrastructure is compute and data. Now, we call it infrastructure because we think that compute and data, it's not only about building it, it's about maintaining it and then deciding how and when to use it appropriately. But there is some kind of useful nuance in this space that we'll come back to perhaps in the group discussion. So compute, for example, I think people worry about the amount of compute you need to have for AI for science, I think with good reason. But equally, some AI for science models, like AlphaFold, for example, are actually quite small in size. And other models, like in weather forecasting, they're quite big, but the AI models are actually more efficient than traditional methods of doing it. So there is some kind of nuance by use case here. Then you get on to actually doing the research. So one thing we've seen across AI for science efforts is they're often, by definition, interdisciplinary. And so what you see in science for a long time is a desire to promote cross-disciplinary research, where you bring together people from different fields. This is a very logical goal because often the biggest breakthroughs in science happen across fields rather than within fields. But the problem is that many of these cross-disciplinary efforts fail. And we saw this again during COVID-19, where many were spun up. And they fail because people often stay in their own lane, so to speak, and they fail to achieve true kind of genuine interdisciplinarity. And so what we've seen in the efforts that work best in the application of AI to science is that you see like real team-based science, where people come together from different backgrounds, but really develop shared methods. And so the question is that how do you use AI to encourage more genuinely interdisciplinary work? And there's many ways to organize science research to do that we can also come back to perhaps in the group discussion. The final ingredient over here on the right-hand side is adoption, right? So you might think that if you train a very good AI for science model in protein design or material science or weather forecasting, that every scientist will use it. And we have discovered that isn't the case, right? Actually, to get scientists to use AI models, they often will need certain kinds of access modalities, so like databases or servers that are designed for scientists. There's a question again about how do you do that work best and how do you incentivize that work best. But also scientists often need training to use AI models and certainly to fine-tune them for more advanced use cases. And so again, for our side, we've worked on some training programs for scientists. For example, how to properly use AlphaFold, how to understand certain complex aspects of it. So for AlphaFold, every protein comes with a confidence score attached to it. So we wanted to kind of say to scientists, help them understand what do these scores mean, how should it affect their research, and so on. So we see many use cases for AI in science where scientists require targeted training. And then underpinning all of these ingredients, for us at least, is two things. So one is partnerships. So in almost every Google DeepMind AI for Science project, there's normally a partner of some shape or size, often from academia or from a public research institution. And they help across the whole life cycle, from specifying the problem to creating the data to actually doing the research and releasing it into the world. And we often also spend a lot of time thinking about risks and benefits from the work to science and to society, which I'll come on to in the next bit. So I'll briefly talk about now the 5 risks that we see in this area, and then a few policy ideas, and then I'll pause for kind of wider group discussion and conversation. The risks, we wanted to address kind of head on the fact that people, especially scientists, are worried about the application of AI to science in many ways. So we're starting to see in the last couple of years the first kind of good surveys of scientists about AI. Not only how are they using AI or not using it, but what are they worried about? I think these 5 areas capture what they're worried about. And you'll interestingly see that safety is not there. Of course, some scientists do worry about safety, absolutely. Even though safety is a big topic in the broader AI policy debate, I think scientists tend to focus more on other things, especially how will AI affect the practice of science and the goals of science. So the first thing they're worried about is the effect on scientific creativity. So again, if you look back at the history of science, many breakthroughs appear to be the result of human intuition, or kind of a human or a team of humans having an unorthodox idea that went against the grain of the time, or just like serendipity. So like studying a certain problem and finding a solution to a different problem, right? And what people worry about AI is that we're going to have a system of science where we train AI models for very specific scientific tasks. And in doing so, we might lose this human creativity that has served us well over the past century. The second concern they have is around reliability. So obviously much of science depends on science itself being self-correcting. If you're a researcher or a practitioner, you are researching a certain paper or the evidence base, you need to be able to trust that it's reliable. That is, that it's kind of free of error or free of bias. And of course, what people worry about with AI in particular is the hallucinations problem. And the fact that AI might hallucinate not just scientific outputs, but also in particular citations, which is a real problem for many large language models so far, including our own ones. A third risk people worry about is scientific understanding. So here the concern is that, yes, AI can maybe help us to predict the structure of a protein or to predict the weather, but will it tell us why a protein falls a certain way? Or will it tell us why the weather is the way it is? And this is a kind of part of a wider debate, of course, about what is the true goal of science. For some people, it is this deeper understanding. For other people, it's more about controlling the system, being able to predict it, and then being able to intervene on it. And those goals are sometimes kind of orthogonal. So we have drugs, for example, that work well, we trust them, we don't necessarily fully understand how they work. But with AI, people are worried that they see the lack of explainability and opacity in deep learning models will undermine our scientific understanding, even if we get new breakthroughs from it. Final 2 risks of concern are equity and the environment. So equity is basically the concern that across different groups, whether it's across different countries, languages, genders, ethnicities, in science today, we often see some groups are represented more than others, whether that be in the practitioner base, whether it be in the data that underpins science, whether it be in the experiments that people carry out. And of course, then downstream, it means that science benefits some people more than others, and also hurts some people more than others. And some people worry that AI being used more in science could exacerbate that. For example, the AI practitioner base is not particularly diverse, even though many folks, including ourselves at Google DeepMind, are trying to change that. And so people worry that if you apply AI more in science, it might kind of hurt the broader diversity in science itself. The final one, the environment, of course, I think people know there's deep concern about will AI and the compute used to train AI models and to run them, will it lead to a worsening of greenhouse gas emissions, as well as a worsening of problems like water use, for example, due to the water used to cool data centers. I'll quickly sort of summarize our quick take on this. Our take on this, my personal take on this, which will sound very techno-solutionist, is I think applying AI in science will be net beneficial to all these 5 areas over the next 5 to 10 years. I'm kind of particularly optimistic about creativity, reliability, understanding in the environment. I think equity will be harder for many reasons. But the main reason I'm optimistic is really twofold. So one is that for many of these problems and risks, there are mitigations underway. So we see this perhaps most clearly for hallucinations, where there's much work underway in AI to bring down hallucinations and lots of progress already. I think the more important reasons that all 5 of these areas, they're often discussed as kind of like stable, idealized constructs, like things that are doing quite well in science right now, and AI is coming along to pose a risk to them. Whereas in reality, many of these areas face big challenges, and I think AI could help address some of these challenges if we use it in science. So just to give one example for reliability, again, today, the reliability of scientific information faces many challenges, right? We have p-hacking and publication bias. That means that we publish much more positive results than negative ones, which skews the research base. We have cases of fraud. We have cases of mistakes, especially in the use of statistical methods. So there's many problems affecting the reliability of the scientific research base. And we're already seeing some examples for how AI could address some of these problems, like using AI to examine the evidence that could support or detract from certain scientific claims. So I think we'll start to see more examples in the near term about how AI is boosting scientific reliability rather than hurting it. And I actually think that we'll see that across all 5 of these areas. But again, I won't go into it for now, just for time. So final slide, given all of this, what should policymakers do? So I think we landed on four ideas that policymakers could do that would ensure that the application of AI to science is as good as possible, maximizing the upside, reducing the downside, and making sure everyone can share in the benefits. So one is around problem selection, focusing attention on what are the most important problems that AI is useful for in the scientific realm. So we call these the Hilbert problems. So you might know that in mathematics, the German mathematician David Hilbert, back in, I think it was 1900, came up with a list of 23 problems, unsolved maths problems, that were then hugely influential in steering maths over the next century. And that's the question we have, is what list of problems could steer the application of AI for science, in the next 20 or 30 years? On the data front, how can we make data sets more available to train AI models? In some cases, will mean making existing data more available. So we see examples all the time of data in the science world that is not public, or not accessible, or not usable, or not at the quality level you need to have to be training AI models on it. We also see ideas for how you can create whole new data sets. One area that I'm very excited about is digitizing the scientific archives to make them usable for training AI, where we've seen some cool projects recently, including funded by governments in partnership with the private sector and civil society. On the skills side, as mentioned, you think about how we can give short-term targeted skills programs to scientists to help them use AI today, while also rethinking our education system for the longer term, so that we have more scientists coming out who are sort of AI native and comfortable working across disciplines with AI. And then finally, organizing science. There is no kind of iron rule that says we have to organize science research into either academia or public research institutions or private labs. We get to decide collectively what kinds of organizations we need to enable the application of AI for science, whether it's organizations that are created to build and maintain certain data sets or evaluation methods or new kinds of tooling or skills programs. So I think we can experiment a lot more with how we organize science to make it kind of amenable to the application of AI.